Come on, this is the worst. Now this is a breadboard, and you have probably seen one before, because pretty much everyone on the internet uses them for their electronic circuits. And to be fair, in theory they are amazing, because pretty much every component fits on there, you can easily create circuits using some wire, and you can reuse them again and again. So they should be the perfect prototyping tool, right? Well, if you watch my videos, then you know I often avoid them completely and instead create such beautiful circuit sculptures, where I basically connect the components in mid-air using solid core wire. And yes, I get lots of comments about this. Some people love it, others think I'm crazy. But I stand by it. This is way better than using breadboards. But is that actually true, or am I really just crazy? To find out, I bought myself 3 breadboards at different price points, going from cheap to quite expensive. And in this video, I will conduct 3 scientific experiments that will show us once and for all whether breadboards are really as bad as I think they are. Let's get started! Now, breadboards are of course important for an electronics video creator like me, but what is also important is storing all my video files safely and having tons of storage. And that is why so far I've been using this NAS DH4300 Plus from UGREEN, who are actually the sponsor of this week's video. They also sent me and let me experience their latest NAS, the DXP4800 GT. Here's what I love most about their NAS products. Their data speed is crazy fast. The DH4300 Plus only has a single 2.5G port, while the GT has been upgraded to dual 10G ports. That means I can use my video files directly in my editing software. They also offer UGOS Pro, and thus you can easily back up all of your phone's data. And probably the best is the easy to use user interface and Docker integration, meaning I can install something like Jellyfin and create a backup of my entire movie library. Awesome! If all of that sounds good to you, then the UGREEN NAS GT series just launched with an exclusive 10% discount that you can grab by clicking the link below in the video description. Now before we start, I have to admit that so far I've only been using the cheapest of the cheapest breadboards, for the very simple reason that I didn't know it any better. I mean, when you search for breadboard on Amazon or AliExpress, you pretty much only get these cheap options and nothing else. That is why my first test subject will of course be such a cheapie for around €3. But if you dig deeper and search for actual recommendations from other people, then you often get pointed to this BB830T breadboards that cost 3 times more than my cheapie, and this 3M breadboards that cost 24 times more. These 3 will be my candidates for all the tests. So let's start with the first one, that is probably the most important one, all about loose wires. You see, when creating a circuit on a breadboard, then we basically connect the pins of the components to one another by using these push-in metal connectors. They clamp down on the pin or wire and hold it tight, which initially sounds great, but for me it very often happens that such a connection does not make proper contact. Thus your final circuit might behave strangely or not work at all, and good luck finding the loose connection, because the bigger your circuit gets, the harder it is to find. Now of course, tapping on the circuit to see when it glitches is not the most scientific method. So instead, I placed an ESP32 on the cheapest breadboards and connected 8 of its inputs via pull-down resistors to ground. That means if all connections are there, these inputs are pulled down close to 0 volts. But if we got a loose connection, then the input jumps up to 3.3 volts, because they're internally pulled up. These are the glitches we want to capture, and to do that more easily, the ESP32 keeps track of the pins jumping up to 3.3 volts. But of course, tapping on there is still not scientific, which is why I got myself this adjustable vibration motor that can, vibrate. I created a small platform for it that my breadboard can sit on, and I admit it is not the very best setup, but it is at least more precisely repeatable than tapping. So I let this thing run for 1 minute while counting the glitches, and since the breadboard is reusable, I afterwards simulated some usage by pulling out and pushing in all connections 20 times. After that, I repeated the vibration tests, and to my own surprise, no glitches were detected in both runs. The reason for that though were these premium resistors that come with pretty thick leads. Usually your resistors come with way thinner leads, just like many other components or wires. And speaking of wire, never trust these jumper wires that are often included with breadboard kits. They come with very little actual wire inside, and I often experienced that the head comes with a loose connection. So to minimize problems, always think about what you plug into your breadboards. But anyway, I repeated the same experiment with resistors that come with thinner leads. And would you look at that? After the first test, we got around 750 glitches. And after once again simulating usage, we got 14,000 glitches. Meaning I'm not crazy and this is truly a problem. At this point I was expecting the more expensive breadboards to come with similar problems, but less severe. However, I was really surprised to find out that the more expensive breadboards delivered no glitches whatsoever. Meaning maybe my whole life I was just missing a good quality breadboard. But either way, such loose wire problems do not exist at all when doing my point-to-point soldering technique. But there are more problems when it comes to breadboards, which brings us to the max current tests. Now I doubt that many people will use them for power electronics, and thus will only draw little current. But it happened to me that things got too hot and thus the plastic melted. But in theory, these metal bus bars should be able to handle quite a bit of current, right? The problem is once again not only the metal though, it is the clamp connection that introduces an additional contact resistance. So for testing, I will be using these jumper wires that came with the most expensive breadboards, and that honestly look pretty good. I insert one at the start of the row and one at the end, and let 5 amps of current flow through there, while measuring the voltage drop as close as possible to the clamp connection. Once I got that measurement, I once again pull out and push in the wires 20 times to simulate usage. Then I measured the voltage drop again, and of course repeated this test for the 2 more expensive breadboards. And I gotta say, I was once again surprised by the results. As it turns out, the cheapest breadboard comes with the lowest resistance, and the most expensive one with the biggest. However, we can also see that the clamp connections are better with the more expensive breadboards, since their voltage drop barely changes after simulating usage. And truth be told, even the biggest resistance is still low enough to handle quite a bit of current. But we should probably stick to this breadboard's datasheet that says 2 amps max. And once again, this is all not really a problem when using my technique, because the contact resistance is minimal and you only have to make sure that the used wire is thick enough. But anyway, last but not least, when it comes to breadboards, we got the problem of parasitic capacitance. This problem occurs because the metal bus bars are very close to one another with an insulator in between, which is basically how a capacitor is built up. Now when using an LCR meter to measure this capacitance, then you can see that we are in the picofarad region, which is pretty small. And by the way, the cheap and slightly more expensive breadboards feature around 2 picofarad, while the most expensive one is close to 3 picofarad. And when doing low frequency circuits like this 555 timer here, then this parasitic capacitance is not really a problem at all. But when you're working with signals that go up into the megahertz region, then you can actually probe the bus bar next to our actual applied signal and see that due to the parasitic capacitance, the higher the frequency goes, the more the signal gets coupled. And once again, by using my technique, this capacitance can be minimized, even though 2 or 3 picofarad are usually no big deal. But of course I have to admit that my technique is definitely more messy and requires more time, which is why for basic circuits I also often use a breadboard. And after all my experiments today, I not only feel like the middle ground is my overall winner, but also that I probably should have used it way sooner to save me lots of headaches over loose wires, and I probably wouldn't have gone crazy over it. With that being said, I hope you enjoyed this show and learned something new. If so, don't forget to like, share, subscribe, hit the notification bell, and consider supporting this show on Patreon to keep it going. Stay creative, and I will see you next time!